Hello, beautiful people, and welcome back to Unit 2 of Regents Chemistry, which is Atomic Concepts. Today, we will further our discussion on electron configurations, and we'll talk about the bright line spectrum. So, have you guys ever looked at the fireworks and wondered that why do you see all those different colors? Or whatever chemical we have in that thing, why are they producing those colors? Well, if you have, then this lesson is your answer to that question. So what happens is that, let's say we are looking at an atom and we provide that atom with some sort of energy. Now, when the electrons of that atom gain that energy, they become excited. And as they become excited, remember the Bohr's model? Remember Bohr said that each orbit has like fixed energy. So now that the electron is getting more and more energy, it cannot stay in that same energy level anymore. So it gets excited and moves up to a higher energy level. Eventually, that electron will release that energy and return back to its original state, and that process is called de-excitation. And when it does that, it releases some energy. So the bottom line to remember here is that when electron absorbs energy, it gets excited and moves to a higher energy level. When electron returns from a higher energy level, it releases energy, and that could be in the form of light, heat, or anything of that sort. And then it comes back to its lower energy level. So ground state is basically like the general state in which the electron is normally found. And this is when we talk about the ground state configuration, then that's the configuration that you find on the periodic table for any element. So for example, when we look at fluorine, its ground state configuration would be 2, 7 because it has 9 electrons. So the first 2 are going to be in the first orbit, the next 7 are going to be in the second orbit. Excited state, however, is like the state of the atom for like a very small period of time when the electron absorbs energy and it moves to a higher energy level. So during that stage, however, when we have to write the electron configuration for the excited state, it does change, and we have to indicate that this is how the electron moved. So for example, let's look at sodium. The ground state configuration, the one that you find in the periodic table, is 281. Now, when one of the electrons in sodium gets excited, let's say we have an electron in the second orbit that gets excited and now it has to move to a higher energy level, and we'll just assume that it is moving to the third orbit. So the excited state configuration would then become 2, 7, 2. So we'll have 7 electrons left in the second orbit now because one of them left and moved to the third orbit, and then we'll have 1 extra electron in the third orbit because the one that moved from the second is now in the third. But then remember, excited state is like that state of the atom for a very short amount of time, and then eventually the atom just returns back to its ground state, and when it does that, energy is released in the form of heat, light, and that good stuff. So let's quickly practice how can we write the excited state configurations for some of these elements. So when we talk about magnesium, look at your periodic table. Look at the bottom left corner for magnesium, which is Mg. The ground state configuration is 282. Now let's say that an electron from the third orbit moved to the fourth orbit. This is what the excited state configuration can look like. Sulfur, the ground state configuration, the one that you see in the periodic table, is 286. Let's say that one electron from the third orbit moved to the fourth orbit, or one electron from the second orbit moved to the third orbit. So any electrons out of these can move. The only thing that you have to take care of is that you are not exceeding the maximum limit for any orbit that it can hold. But you can definitely, as long as you're not disrupting that rule, we can move any electron to write the excited state configuration. So in this case, I chose to write 2851 because I said one electron moved from the third orbit to the fourth orbit. Then we have nitrogen. This is what the ground state configuration looks like. Let's say that one electron from the third orbit is from the second orbit moved to a third, so that would be the configuration. You can also choose to move an orbit from the first orbit to the second, so that would then be 16. Argon 288. Let's say that one electron from the last third orbit moved to the fourth orbit, and that gives us 2871. Okay, so this is how you write the excited state configurations. Now, for this class, we will be doing the flame test lab, and what we do in the flame test is just we take like a bunch of different chemicals and we burn them and we see the color of their flame. And each element is going to produce a different color, and that is basically what explains how all of them release energy, release that light, release that color at different wavelengths. And this is exactly what happens in the fireworks, because depending on what type of chemical is being used in the firework, it is going to produce a different color, because each chemical is going to produce that color at a different wavelength, and then which is why that color is going to be different. So that produces a bright line spectrum, which, remember, and this is a very, 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 very important concept, comes a lot on the regions, that when or how is a bright line spectrum produced. Remember, energy is not released when an electron is moving from lower energy level to a higher energy level, because that is the point when it's only getting excited. So electron gets excited, moves from a lower energy level to a higher energy level, and it needs energy to do that. But when it comes back from the higher energy level to the lower energy level, that's when it's relaxed, and that is when it releases that energy. That is when it emits that light or heat, and that is when that bright line spectrum is produced. Okay, and we use the bright line spectrum to basically identify different elements, because again, all of them are going to release light at different wavelengths. This is what the bright line spectrum looks like. All this is telling you is that each of these elements is releasing a light, a color at a different wavelength, which is why those lights have different colors. So the type of question, another type of question other than the question that how is a bright line spectrum produced, you also get a question like this, where you just have to, so here you see the bright line spectrums for lithium, cadmium, and strontium, and then you have a mixture at the bottom, and you have to identify that which one, two, or maybe all three of them do you have in the mixture. So all you have to do is just match your lines. So start with the first line in the mixture and try to match that with whatever element you can match that with. So here I can match this first line with strontium. I can match the next line with strontium as well. The next line in my mixture is going to match up with lithium. Next up is matching with strontium again. Then we are matching up with lithium again. And I definitely skipped that one line in the middle, but that is also matching with lithium. And just a little bit with cadmium. Then we have these three lines matching up with strontium, another line matching with lithium, and two other lines matching with strontium. So it turns out that all of the lines in strontium and all of the lines in lithium are matching with each other. However, there's only one line that is briefly matching with our mixture in cadmium. So your answer will be that our mixture contains lithium and strontium. Okay, so that's how you solve a question like this. So that is it, guys. We are done with the electron configuration part. Now we just have one tiny bit of this chapter left, and I will see you guys next time for that.